Okay, good morning. Please scan the QR code and do the View Padlet quiz questions first. Okay, now let's look at the first one together. So what it says here is that the MSFE, which is the mean square forecast error for the optimal long-run forecast of a stationary time series, converges to the series long-run variance, because in the long run, the best prediction is the series mean. Is this correct, or is this a false statement? Okay. So the majority wins. Okay. Now, to see this, those who just joined, you can scan the QR code. So remember last week we've established that the optimal forecast, which is the yt plus h given information at time t, is essentially the conditional expectation of this future observation given all information available at time t. And we know that as h goes to infinity, this will converge to the long run mean, mu y, which is essentially the expected value of yt, given that it's stationary. Okay, now, because it's stationary, basically it means that the mean is constant over time. So the conditional expectation of yt must be the same as, the expectation of yt must be the same as the expectation of the future observation, y capital T plus h. Now, the MSFE of the optimal forecast, which is essentially the expected value of the square of the forecast error associated with this forecast. Now remember, the forecast error is essentially the difference between the actual value of the future observation and the optimal forecast. Okay, then essentially the MSFE, okay, which is the expected value of the forecast error square, must be the same as the expected value of the square of this difference. Okay? Now, we know that in the long run, the optimal forecast essentially converges to the mean, y, the expected value of this future observation. Okay, this is as h goes to infinity. Then essentially, that means the MSFE will become the y capital T plus h minus its expected value. Okay, we take the square of this difference and then take the expectation of this square. But this is precisely the definition of variance, okay? And given stationarity, the variance is constant over time. There's only one value for the variance, which is precisely the sigma square y, okay? So this is correct. The MSFE for the optimal long-run forecast of a stationary time series will converge to its variance, okay? Because the optimal long-run forecast itself is the mean of the series, okay? So this is the first statement. Now, the second one. So what we have here is that a time series that exhibits mean reversion will have a constant autocorrelation function over time, regardless of the time lag. Okay, can this be correct, or it's actually a false statement? Okay, this should be quite straightforward. It's incorrect. Given that it's mean reverting, then the correlation or the covariance between the observations as they become further and further apart should go down, okay? So the covariance between yt and yt minus 1 should be greater than that between yt and yt minus 2, and be greater than that between yt and yt minus 3. So the past has a diminishing effect on the future, okay? And that's why we have mean reversion. A shock hitting, let's say, the series at time t, the effect of the shock will diminish, will fade away as time passes. Then, in the long run, the time series, if it's mean reverting, it will revert to its own mean, okay? So this is a false statement. We require a autocorrelation function that reduces as h increases, okay? But it doesn't need any restrictions on the speed of this diminishing rate, okay? So regardless of its diminishing quickly or it's diminishing slowly, as long as it is diminishing, then we will have mean reverting, okay? So mean reversion and persistence isn't really the same thing. Persistence is about the rate of this, about how fast this sort of decaying behavior sort of evolves as h increases, whereas mean reverting is just about that it is decreasing regardless of how fast or how slow it is. So this is the second one, okay? This is a false statement. Now, the last one. By now, you should all know what this implies, okay? What is a constant autocorrelation structure? We've tested this in quiz 1 and been talking about stationarity over and over again over the last 4 weeks. So what it says here is that a constant autocorrelation structure implies that the autocorrelation at lag h must remain constant over time. Is this true or false? Okay, apparently this must be a true statement. The constant structure basically requires that the autocorrelation at any given lag to be the same regardless of the time location. Okay, regardless of it's in 2000 or it's in 2020 or it's in 1,000 years later from now, the autocorrelation between two observations that, let's say that's 10 periods apart, has to be the same. Okay, if the autocorrelation between YT and YT minus 10, it's let's say 0.5 in 2000, 1,000 years later in the year 3000, we require it to still remain at 0.5. It's about the structure, okay? But of course, we don't impose any restriction on that the autocorrelation at different lags to be the same. Okay, we only require that given a lag, it has to remain the same regardless of the time location. Okay, but that the autocorrelation at different lag values to be the same is a more restrictive condition, and that's not part of the requirement for stationarity. Of course, they can be the same, just like the white noise process, okay? The autocorrelation, regardless of the value of H, is always 0. That's perfectly fine. The white noise is always stationary. But, okay, this is not a requirement. Okay? It's not part of the defining condition for stationarity. So these are the 3 Padlet quiz questions to kick off our lecture today. Now, before we look into non-stationarity, just to quickly wrap up on what we discussed last week. So on Friday, we talked about computing the pseudo out-of-sample MSFE, okay? That's basically an iterative process. So we basically reserve the final, let's say 20% of the sample as if it's pseudo out of sample, pretending we have not seen it, and that will allow us to compute the forecast error, which in practice is never known, but because we actually observe it, because we're pretending it is unknown, so we can compute the pseudo OOS forecast error, and that allows us to compute the pseudo OOS MSFE, okay? Now, the whole idea of computing the pseudo OOS MSFE thingy is really to allow us to compare the performance of different models when we use them for forecasting. So here, this is applied to our familiar data set, the GDP growth. So essentially, the entire data set spanned from 1957 Q3 to 2013 Q4. So there's a total of 226 observations. And then we reserve the final 40, there's a final 40 observations as if the pseudo out of sample, okay? And then essentially what we're doing is, so what we have is from 1957 Q3 to 2013 Q4. What we're going to do is we're going to reserve the sample starting from 2002 Q1 and pretend this as the pseudo out of sample, okay? This is the essentially observations that we're going to forecast. Then in order to compute the pseudo MSFE associated with the one step ahead forecast, okay, essentially we want to forecast 2002 Q1, and we want to do a one step ahead forecast for this observation. So what we do is, okay, here we have the 2001 Q4. We use all the data up to 2001 Q4, starting from 1957 Q3. We estimate the sample, okay, we estimate the sample, and this will give us some alpha hat, and this will allow us to compute the visible one step ahead forecast, okay, where this capital T is equal to 2001 Q4. And this is forecasting the 2002 Q1. And by doing this, this gives us one visible forecast error, okay? Then the next step is we'll update the sample. So remember, we are only concerning one step ahead forecast. So the next step is we will expand the previous in sample by one observation. So now we will expand this up to 2002 Q1, okay? And then we're going to re-estimate this new sample that give us some other alpha hats. And then using these alpha hats, we can again compute the so-called one step ahead forecast, okay? We have the y hat t plus 1 given t, where this capital T is now 2002 Q1. And we are forecasting the 2002 Q2. So here we have the 2002 Q2. The value here is forecasting the 2002 Q2 observation. And then this will give us another forecast error associated with this visible forecast. And then we just consider continuing this process up to the final period. Then essentially, we will have 40 pseudo out of sample forecast, which gives us 40 pseudo out of sample forecast error that allowed us to compute the MSFE, okay? So this could be done for different AR models of different orders and also for different forecasting horizon H. So you can see in the table here, basically the top row correspond to different forecasting horizons, whether we're doing one step, two step, up to the eight step ahead forecast. And then we're comparing the performance of AR models starting from order 1 up to order 6. And all these values in the table is the root MSFE. So it's the standard deviation of the not the standard deviation. It's the square root of the MSFE, okay? And remember previously, before we even start looking at forecasting, we talked about model selection. We talked about stepwise downward, we talked about AIC, BIC, adjusted R-square. Remember back then, AR2 was the chosen optimal model. The stepwise procedure, the AIC and BIC, they all have chosen P equal to 2 to be the optimal order. And we can also see in this table that the MSFE associated with the AR2 is the smallest across all AR models, regardless of the forecast horizon, okay? So if we were to forecast future GDP growth using the data set and the present analysis, this hint at we should use an AR2 for more reliable forecast if we are comparing against a set of AR models from order 1 to 6, okay? So this is the comparison. So how actually is the MSFE computed? So basically, this figure here sort of resembles what I'm doing on my iPad, okay? So the solid line is the actual GDP growth for the pseudo out of sample period. So in practice, we never observe this solid line because this is actually the genuine future. But here we're just pretending that it is the future, but we do observe it. And the dashed line is the one step ahead forecast, okay, that we obtain for each time point using the pseudo OOS approach. Okay, so 2002, we use Q1, we use all information up to 2001 Q4. For 2002 Q2, we use all information up to 2002 Q1. So the difference, the gap between the solid and the dashed line basically represents the pseudo-visible forecast error for the one step ahead forecast at each time point. Then the MSFE is basically, we take the square of each of these gaps and then sum the square, take the average, okay? So This is just kind of a visualization of what the forecast error is when we compute it via the pseudo-OS approach. So that's all about forecasting. And starting this week, we're going to start on a new chapter, non-stationarities. We'll be basically looking at different types of non-stationarities. How can we handle them, or how can we transform them to make them stationary? So before doing that, let's do a quick recap on what actually is stationarity. So the defining characteristic of stationarity, the stationarity that we are considering this term, is the weak stationarity or the covariant stationarity. Basically requires that the statistical properties, okay, the mean, the variance, and the autocorrelation structure to remain constant over time. So basically, the constant autocorrelation structure, just as what we did for the quiz just now, implies that the autocorrelation depends only on the lag value h, okay, but not the location in time. The time index t should not be involved. Now, it seems to me that a lot of you are confused about the persistence and stationarity, what actually is the relationship between them. So the first thing you should always keep in mind is that they do not directly imply each other. Basically, they tell us some information about different aspects of the underlying time series. The stationarity focuses on constant statistical properties. It's about the pattern, the behavior over time. Whereas persistence is about how strong or lasting the past values influence the future observations. Okay? It's about the h, how the correlation between the two values evolve as h increases. The time t, okay, the time index t is not involved in the discussion of persistence alone, okay? So they basically tell us different aspects. A stationary time series can have strong persistence. It can also have weak persistence. And similarly, a non-stationary time series can have strong persistence, but it can also have weak persistence. So they do not imply each other. So as an example, okay, basically weak persistence means that we will observe a rapid decay in the ACF plot. Okay, so we have a quick diminishing rate of the past, the effect of past influencing the future. And this can be consistent with non-stationarity. Okay, so if you look at the graph here on the left, we have the daily return on the stock price index. Okay, while this has a constant mean because it fluctuates around the same value, which is precisely 0, an immediate takeaway here is that it has a changing variance. There are periods, let's say between 1993 and 1998, that it has a smaller volatility, but we can also see that from 1998 to roughly 2003, the time series has a greater volatility. Basically means that the variance is changing over time, so it's not stationary. But if you look at the ACF, okay, except for the first bar, which is always 1 because it's the correlation with itself, given that it's lag 0, okay, we can see that essentially there's no autocorrelation between any two different time periods, okay. T is not correlated with its T-1, T-2, or T-3, so it has weak persistence. Essentially, the past does not influence the future, okay. So non-stationarity can accommodate weak persistence. And similarly, if we look at strong persistence, basically that means that the ACF plot will show a slow decay. So the past has a prolonged effect on the future. But this doesn't necessarily imply non-stationarity, just like the AR1, okay? And AR1 with the autoregressive coefficient alpha 1 being 0.9 is still considered stationary because it's below the cutoff 1, okay? You can see that it's still mean reverting, albeit at a slower rate, okay? And the ACF plot contrasts to the stock return, shows a very immediate pattern of a slow geometric decay. So the AR1 with alpha 1 being 0.9, it's stationary, but it has a strong persistence, okay? So persistence and stationarity do not directly imply each other. They tell us different information about the underlying time series, and you should be careful when you attempt to interpret the time plot and the ACF plot. Okay? So one is about the constancy of the statistical property, and another one is about the continuing effect of the past influencing the future observations. If you really want to relate persistence with stationarity, then the constant autocorrelation structure, which is one of the defining characteristics of a stationary time series, basically requires that the strength of the persistence remains constant over time. If we observe weak persistence in 2000, we should observe the same type of weak persistency in 3000, okay? Basically what it implies is, if we observe something like this, okay, in 2000, had we had a sample for 3000, we should get the same ACF plot, or at least similar. So the strength of persistence remains constant over time. And this is consistent with the requirement of constant autocorrelation structure. Whatever this level of persistence is, be it strong or weak, it should not vary with the time index t, okay? So this is about the stationarity and persistence. Now, one final thing before we start talking about structural break. So one has to be cautious about visual inspections. Whatever you see from the time plot or ACF plot, these are only initial visual inspections. They cannot give you formal conclusions. Any formal conclusion has to be made via formal hypothesis testing, okay? This is just a starting point at the very beginning of any time series analysis, okay? Visual representation, visual plots has to be coupled with regression analysis and hypothesis testing in order to conclude about the true characteristic of the underlying time series. And another thing is, you have to be careful with the ACF plot, okay? So here, essentially, we have different bars for different autocorrelation at different lags. And essentially, we can see that here we have 35 years, okay, multiplied by 4. That's more than 120 bars that will present on the ACF plot. And each bar essentially is one test, because here we have a 95% confidence interval, okay? Now, given one bar, the significance level, or whatever, the type 1 error rate is 5%. But remember in the discussion of topic 2, when we attempt to do multiple tests at the same time, the overall type 1 error rate is much larger than the defined 5%. Okay, so it could be that when we plot an ACF with so many lags, there could be some bars like the one here at lag 12, or the one here maybe at lag 7. They could appear significant just due to random chance, and you should not over extrapolate the significance. Okay, if you were to interpret the significance, it has to be paired with empirical significance. Observe that, let's say, if we have something like quarter data, okay, and we observe that, for example, the ACF just converges to 0, quickly becomes 0 around lag 4. But then randomly at lag 8, we observe something that's significant. Okay? That could be significant due to random chance, but then because it's a quarterly data, lag 8 basically means 2 years ago at the same time. That might give us some useful information in practice. We don't know, but then in that case, we have to be cautious about interpreting it. We need to pair statistical significance with practical significance, okay? So this is something you should be careful when attempting to interpret the ACF plot. Now, coming back to our focus today, structural breaks. So we've been talking about this AR1 over and over again, where we have the error terms, the shock following IID white noise, and that is independent of past information. And we also know that if the autoregressive coefficient alpha 1 is less than 1 in absolute value, then it's stationary. Now, given the structure, how can we possibly accommodate non-stationarities? So remember, stationarity requires all three conditions to satisfy simultaneously: constant mean, constant variance, constant autocorrelation structure. Then to have non-stationarity, we just need to break one of the three conditions, okay? Let it be a changing mean, a changing variance, or a changing autocorrelation structure over time. Then essentially, structural breaks is about a sudden change in the behavior of the time series data. It's just a one-off change, and the effect of that one-off change is permanent, okay? Let's say previously the mean were 5, and then there was a sudden change in 2002, and then the mean became 10, and stay at 10 forever, okay? In the long run, this is non-stationary because the mean has changed, okay? But then if we look at the sample data between 2002 and after 2002, it remained stationary within each subperiod. So essentially, this sudden change in the behavior will sort of cause an unexpected shift in the statistical properties, let it be the mean, the variance, or the autocorrelation structure. And more importantly, these kind of sudden changes in time series, which is often macroeconomic data, they reflect structural changes in the underlying economic condition. So an example here is the US real GNP, the gross national product growth. Okay, so on the left, we see the real GNP, which is similar to the US real GDP. It's non-stationary, having an upward trend. But by taking the difference, okay, we stabilize it and get the quarterly growth rate, which is something that we're interested in looking at today. So in a sense, it's more stationary compared to the real GNP because we can see that there's no obvious trend in the growth rate. But can we really conclude that it's stationary? If we look at the time plot, we can see that before the 1990, it has a greater fluctuation, and it seems to have a higher mean compared to after the 1990. And this could possibly be due to, financial market liberalization, globalization happening back then. So we suspect that there is a sudden change in its underlying statistical properties. And if we attempt to plot the ACF or compute the sample mean and the standard deviation in the two time periods, okay, between 1970 up to 1989 Q4, which is before the 1990s, and also for that after the 1990s, apparently we see that the ACF plot shows different pattern, okay? Basically, that violates one of the requirements, okay, that we have just discussed. If it has a constant autocorrelation structure, then the strength of the persistence should remain constant over time. But obviously it's not. It has a weaker persistence before 1990, whereas it has a higher persistence after 1990, okay? And we can also see that the mean pre-1990 is 8.59, higher than that post-1990, which is 4.76. And the earlier sample also is associated with a higher volatility, so standard deviation being 4.14, and the subsequent sample has a smaller fluctuation, where the standard deviation is only 2.74. Okay, so visual analysis suggested that there is a change in parameters after the 1990s. So it suggests that there might be a structural break. But is the visual inspection statistically significant? In order to know that, we need to do some formal statistical test, okay? So essentially, the break is an abrupt change in the model parameters at a specific point in time. And typically, in regression analysis, we model this using breakpoint dummies. So we use a dummy variable to represent the point where we suspect break to happen. Then, given that we suspect that there is a break happening in 1990 Q1, essentially, we will incorporate the breakpoint dummy, the dt tau, okay, where this is a dummy variable that is equal to 1 if the observations happens on or after 1990 Q1. And this dummy variable is equal to 0 if the underlying observation associated with the index t is smaller than the 1990 Q1, which means it's before the break, okay? So this is a dummy variable defined for the break date tau, where this tau here is the 1990 Q1. So 0 before the break, and on the break or afterwards, the dummy is 1. And we incorporate this dummy variable into the AR1 model along with an interaction term, okay? So this is to capture both the change in the intercept and also the change in the slope. So this is applying what we've seen in topic 2 to time series. We talk about dummy variable, we talk about their interaction term, how that induces a change in slope and a change in the intercept between two groups. Here, the two groups is just that one before the break and another one on or after the break, okay? Then, essentially, the intercept changes from alpha naught, okay? So we have that so we have the AR1, and we now include the dummy for the break, and also an interaction term between this breakpoint dummy and the immediate lag. Then for the subsample before the break, okay, which is before tau, that is 1990 Q1. Then essentially for this subsample, okay, dt of tau, the time dummy is just 0, okay, because these t's are smaller than tau. Then for this subsample, okay, we have our A model becomes just the alpha naught plus alpha 1, yt minus 1, plus gamma naught times 0, plus gamma 1 times 0 times the yt minus 1 plus ut. Okay, so this is 0, this is 0. There will be no terms involving the dummy. Then we have alpha naught plus alpha 1 yt minus 1 plus ut. Okay, So this is the model for before the break. Now, for the subsample, starting from the break, okay, that is basically on or after the tau being 1990 Q1. Then for these observations within this subsample, essentially the breakpoint dummy is equal to 1, okay, because they happen on or after the breakpoint. Now, this implies if we plug in the value for the dummy into our model equation, we'll have gamma naught times 1 plus gamma 1 times 1 times yt minus 1 plus ut. Okay, so basically that implies the intercept now becomes alpha naught plus gamma naught. And we also have the slope now becomes alpha 1 plus gamma 1 times the yt minus 1 plus ut. Okay? So there's a change in the intercept and a change in the slope. Then, in order to test for the structural break formally, essentially it's about testing the gamma naught and the gamma 1, whether these gammas are statistically significant. Okay? So interested in the gammas. Then basically that is just our usual F-test. We're testing two restrictions, although specifically in the given context, because we're testing for breaks, okay? It's called the Chow breakpoint test, but essentially it's just the usual F-test, okay? So it's for the test, it's testing for the structural break at a known point tau, where here the tau is 1990 Q1. Then under the null hypothesis, there is no structural break exists. Basically, we're testing, okay, gamma naught plus, the gamma naught is equal to gamma 1 equal to 0. Whereas the alternative hypothesis is either one or both of them being different from 0. Okay? So here we are testing Q equal to 2 restrictions. Under the null hypothesis, okay, we have the restrictive model, which is essentially by imposing the gamma naught and gamma 1 being 0, then we just have the AR1, the usual one. Okay. Remember on the previous slide, we stated that this alpha 1 is smaller than 1 in absolute value. So essentially, the restricted model proposes that we have a stationary AR1. Under the null hypothesis, the YT is stationary. There's no structural break. Whereas under the alternative, there is a break. Okay. So the unrestricted model, restricted model is the model with the dummy, sorry. Okay. So the original model, or the model with the time dummies, is the unrestricted model under the alternative. Okay? So given that this is the usual F-test, you should draw the critical value from the FQ infinity distribution. So I've already provided this and uploaded it on Blackboard, okay, our usual statistical tables. You'll find this statistical table under the semester 2 lecture notes, because in semester 2, we also have 2 extra tables. You'll see in a bit. That's for tests in non-stationarities. So here, Q is equal to 2. So we find the degrees of freedom M that is equal to 2. So we want to read the critical values from this row. And if we're interested at 5%, then the critical value is essentially 3, okay? And it will be the same statistical tables appendix you'll see in a semester 2 final exam. So if you reject the null hypothesis, which means that if the F statistic is greater than 3 in this case, then there's evidence for a structural break happening at tau, which is 1990 Q1 in this case, indicating that the underlying time series is non-stationary. Okay? So if we formally test this using the data set for the GMP growth. So first of all, we estimate a model with the dummies and the interaction term. So this highlighted part, the D1 true, basically stands for the dummy alone, okay? So this row gives you the coefficient gamma naught, okay? So gamma hat naught is equal to minus 4.05, and the last row gives you the interaction term. And we can see that here, the gamma hat 1 is 0.21. So this is the estimated result, and remember, we can use the linear hypothesis function in R to test joint hypothesis. So computing the F statistic, which is essentially the child test statistic, for testing gamma naught and gamma 1 simultaneously being 0, we get an F statistic that is equal to 10.4, which is greater than the critical value associated with 2 restrictions, and at the 5% level, we just seen that is 3. Then basically there is strong evidence to reject the null hypothesis of no break at 1990 Q1, which means there is a break and the GMP growth is not stationary. So this is testing for structural breaks at known dates. The next step is, what if we don't know the known dates? What if actually 1990 Q1 is not the actual time where the structural break happens? We'll come back to testing for structural breaks at unknown dates on Friday. So I'll finish the rest of the slides on Friday. Before I let you go, okay, some main stuff. So this week, we have quiz 2, and the information for quiz 2 is already uploaded. Okay, you can find it on the semester 2 assessment page at the bottom. And also, if you have read the announcement I made this morning, I've already made the information for the midterm available. So, about the midterm. Basically, okay, it's almost the same as last semester. So first of all, the midterm covers everything for topic 4, time series, plus some questions on hypothesis testing, okay? And the main difference between this midterm and the last time is we'll now have a set of bonus questions, okay? They're there for you to boost your mark. So the actual midterm, essentially the same as last semester. You have a total of 10 questions. Same as last term, you have a combination of fill in the blanks and multiple choice questions. You have a strict 45-minute limit to complete the main midterm section. Now, the bonus questions. You get a separate Mobius link to the bonus questions. There are only 3. And they are drawn from the Padlet quiz questions we discussed during the lectures. They'll either be the direct repeats, so basically the same as what you've seen in the lecture, or statements that contrast those previously seen. So, which means, okay, if a true statement was discussed in the lecture, you might see a false one in the bonus question, or it could be that a false statement was discussed in the lecture and you'll be given a true one. But in any case, that should be straightforward, given that I've discussed it in the lecture. Okay, so you have 5 minutes to complete this extra 3 bonus questions. There's no penalty for incorrect answers, and it's completely fine if you don't attempt the bonus question. Okay, but each bonus question, if you do attempt and get them correct, that adds an extra 10 marks to your overall midterm grade, provided that you have attempted the main midterm question. Okay? So, and this has a maximum cap at 100. Then basically what it means is, if you get 60 in the main actual midterm, okay, and no bonus attempt, overall score 60, okay. If you get 1 bonus correct, then 60 plus 10, 70. If you get all 3 bonuses correct, 60 plus 30, 90. But if you get 80 in the midterm and all bonuses correct, okay, although 80 plus 30 is 110, however, the maximum score is capped at 100. So even if you get all 3 correct, the overall score will cap at 100 if you score 80. But if you get all bonuses correct, and yet you didn't attempt the midterm set, your overall score will just be 0 because you didn't do the midterm. Okay? So this is the score calculation, and the midterm will be available on Friday, April the 12th, for 3 hours. So basically from 9 to noon, you have 3 hours to complete the 45-minute midterm plus an extra 5 minutes for the bonus questions. You will have 2 Mobius links, okay? They will appear below this section. 1 for the midterm, 1 for the bonus, okay? Make sure